Okay, in this video I want to look at the graph of a logarithm function. And I'm going to start by looking at an exponential function. This is a graph of 2 to the x. And I want to see if I can come up with its inverse function, because we've talked about before that the inverse of an exponential is defined to be a logarithm. That's how we define logarithms, that y is equal to 2 to the x means that x is going to be the log base 2 of y. The input of one function is the output of the other function, and so if our function f of x is 2 to the x, then the inverse function would be log base 2. So they should have the same base, but otherwise the inverse of an exponential should be a logarithm. And we've previously talked about how to come up with a graph of an inverse function. We can use the line y equals x and draw the mirror image, or we can look at the individual points and swap their x and y coordinates. I'll try and do both. So if I take my individual points and swap the coordinates, instead of 3, 8, we'll have 8, 3. 8, 3. Instead of 2, 4, we'll have 4, 2. Instead of 1, 2, we'll have 2, 1. This point is a little lower than it should be. Let's see, instead of 0, 1, we'll have 1, 0. Instead of negative 1, 1 half, we'll have 1 half, negative 1. And instead of negative 2, 1 fourth, we'll have 1 fourth, negative 2. So over a fourth and down to negative 2. Okay, so I need to connect those dots. And something you'll notice about the graph is, if this is going to be a mirror image, sorry, the camera is wobbling because the cat just jumped on the table. If these two are going to be a mirror image, then where this one is getting really close to a horizontal asymptote, this one is going to end up getting really close to a vertical asymptote. And so the negative y-axis is going to be an asymptote. And then also, on the right side, the graph of 2 to the x gets steeper and steeper and steeper. My slope gets greater and greater and greater. On the other hand, when I look at its inverse function, the logarithm, this graph is getting shallower and shallower and shallower. The slopes are getting less and less and less as time goes on. It's still never going to quite flatten out and come downwards, but it is going to get shallower and shallower and shallower as time goes on. Just like this guy we said before, it gets steeper and steeper and steeper. This graph is the inverse of the mirror image, so it should get shallower and shallower. And kind of the reason is, we mentioned before that if you increase x by 1, that means that your y, you're going to have to double your y. If I look at the corresponding logarithm, it's in a little bit weird format, but the y's here correspond to the x's here. So if y is going to go up by 1, you have to double your x, which means I have to go horizontally a very large amount before I would even go up even one step. Okay, let's talk a little bit more about different features of this logarithm graph. And I'm looking at log base 2 specifically just because I can easily find a set of points to look at. But the shape is roughly the same if I was looking at log base 3 or log base e or log base 10. It would maybe be slightly steeper, slightly higher up, but it would still be the same general shape. Sorry, cat was knocking stuff around. Okay, so let's talk about domain and range. And specifically, I'm looking at domain and range of the logarithm function. So our domain, the set of a lot of x's, we can't plug in x's that are negative. There aren't any points when x is negative. We looked at when we were solving algebraically for logarithms, we couldn't actually take log of a negative number. We also can't take log of 0. So our domain is going to be numbers from 0 on up. Our range, on the other hand, is the set of allowed y's. And if I look at y's on my graph of log base 2, it's definitely going down to minus infinity. And you're just going to have to take my word for it that this graph does continue to go up. It just goes up very, very slowly, slower and slower and slower, but it does keep going up. So eventually it is going to head all the way towards infinity, just very, very, very slowly. Okay, other things to mention. We have an x-intercept, which is 1, 0, and that's true for any logarithm. The things I'm writing down, I guess let's just write it this way. I'm not going to be specific and look at log base 2. I'm going to look at log base any number, and same thing is still going to happen. We will still have the same x-intercept, which is 1, 0, or x equals 1. We will not have any y-intercept. Let's see, we have a vertical asymptote right here. That's the line x equals 0 or the y-axis. And let's see, the graph is increasing. As I go from left to right, both functions actually are increasing. So we mentioned before that it's increasing on a particular interval. It's increasing on its whole domain. So we could also just say it's always increasing, or it's increasing from 0 to infinity. Okay, so those are kind of some of our features of the graph of log base 2 of x, which again is roughly the same shape as any logarithm is going to be. Log base any number of x is still going to have the same domain, range, intercepts, asymptotes, and they're all going to be increasing. I guess I'm telling you slight lies. One of these things is not true. I'm assuming that b is bigger than 1. We very rarely look at logarithms where the base is less than 1. If you did, the only thing that would change is this one. It's not actually going to be increasing. But let's not worry about that. Assuming that the base is bigger than 1, then all these things will still be true regardless of which base you pick.